So consider the following situation. You're a data scientist working for some organization. You have collected some data or you have access to some data that you want to make available to others. But you're worried because the data set contains information about people and you think that some of these people might not want to have this information public. What I want you to get away with from this talk today is an appreciation of the threats that you face when publishing not properly anonymized data and an idea of the tools that are available to you to better anonymize data. What I cannot give you, unfortunately, is a fixed toolbox, a set of steps you just need to follow to have a proper anonymized data set. And we will see why this is the case. There's many reasons for why you want to publish data. Currently, there's a strong movement towards getting governments, cities, other organizations to publish data about their work for accountability and transparency reasons. In this case, the city of New York published a data set containing millions of taxi rides. Information on where the taxi ride started, where it ended, and even how much tip was paid. And this data set was used to make fancy visualizations like that, to make analysis on which part of the city is underserved by cabs, or even just to find out if there's a likelihood that I will get a cab at 4 a.m. in the morning when leaving my friend's home. The data set contained a reference to a taxi ID, but not in raw form, but it was MD5 hashed to make sure that you can't identify the actual cab. Problem is, there's only a limited set of possible taxi IDs in New York, so somebody just sat down, auto-generated all the IDs, MD5 hashed all of them, cross-referenced with the dataset, and within 2 hours, that person had completely de-anonymized the dataset. And then you can think of funny situations like taking a paparazzi photo that somebody had taken of a celebrity getting into a cab, taking the cab number from that photo and figuring out where the celebrity went, and even how much they paid in tip. Publishing data is also very common in the sciences. If a researcher publishes the data set that they base their results on, then other researchers can check that these results indeed are correct and can even build their own research on top of them. There was one very famous data breach in Massachusetts. A data set containing health information, that is, information about a person, for example, date of birth and their zip code, who came to the emergency room, and what kind of medical problem they presented with was in this data set. The data set did not contain any social security numbers or names or other obvious identifiers. But a researcher was still able, just by cross-referencing this data set with the voters list, to identify the governor of Massachusetts from that data set. This case made huge waves, and a bunch of the methods I'm going to be talking about today were kind of sparked by this case. Also, legislation has changed since then. So if you want to publish medical data in the US today, you have to follow some stringent rules, and something like this could not happen today. I want to talk now a little bit more about what we mean by sensitive data, what are the threats that could face the data, and then I want to get a bit more practical. Let's take an example data set and let's go through and anonymize it. It is quite obvious that when you talk about anonymization, then you talk about removing information. And now we also want to look in this talk on the utility left after anonymization. Is it worth it? Is it even worth publishing the data set afterwards? Then I have some bad news, and that is that some of the methods that I'm going to talk about in the first part of the presentation are not going to work for some very common data sets. So I'm talking about some alternative approach as well. And finally, I want to finish the talk with some practical tips and standards. What do we mean when we talk about sensitive information? Well, in case of the medical data breach, I guess most of you would not be happy to have information like that publicly available, that people can just look up in a data set what kind of problems you went to the doctor with. But What is sensitive to you in many cases is not sensitive to others, and the other way around. What is considered sensitive even has some cultural component. I guess most people in this room wouldn't be too happy to have their salary information publicly available. In Sweden, on the other hand, information on how much taxes people pay, and by extension, how much they earned in a year, is publicly available information. And things like what taxi I wear, where did I take a taxi, or what books did I rent, or what movies did I watch, is not necessarily sensitive in itself, but it can give some hints on my behavior, on my habits, on my political ideas. Today, I'm going to have a few assumptions that this talk is based on. Number one, we are talking about publishing raw data, microdata, not statistics. What is good with publishing microdata is that people can make visualizations, they can make their own statistics about the things that interest them, and they can even apply machine learning algorithms. Maybe there's some predictive modeling possible with the data set. And privacy requirements for microdata are obviously much more stringent than for statistics. So it's a much harder problem to solve. Number two, we want to minimize the risk for privacy breaches, and we say that we think that everybody has the same risk, the same equal right to privacy. We will see that datasets often contain some smaller populations. In particular, older people are at risk, and we want to protect them just the same. And we say that our adversary is smart, is resourceful, has access to other datasets, might use technology that we are not aware of. And this part warrants some more getting into. So we think that our adversary will have access to additional data. In particular, interesting is if the adversary knows that the target is in the dataset. That is a very, very helpful information. The adversary might have additional data sets. That could be demographics, public information, could also be private information that they might even have gotten through illegal means. And the adversary might also have personal knowledge about the target. Also bear in mind, the adversary it's not a black and white situation. Your adversary could just as well be a journalist who wants to find proof of the wrongdoings of a corrupt politician. It turns out that you need very little information about the person to uniquely identify them. In the US, 63% of people are likely to be uniquely identifiable if you just know their date of birth, if they're a man or a woman, and their zip code. If you have this three information about somebody and you know that person is in the data set, there's a 63% likelihood that you will be able to find exactly that person. And this is exactly what happened in the Massachusetts data set. The researcher, she had these three pieces of information and could just look up the governor in the medical data set. Let's look at this plot. On the x-axis, we have the age of American inhabitants. On the y-axis, we have the percentage that are likely to be identifiable. Let's consider first the blue line, that is the lower line. And remember, we said on average it was 63% that are likely to be uniquely identifiable. We see here that up until 60 years of age, the line closely follows that average, but there's a sharp increase for older people, and that is just there is fewer of them around. If you are 90 years of age, it's very likely that in your zip code you are the only person with that birth date. The second line, the green line, the one in the middle, shows you the likelihood that there's only one other person who has exactly the same setup as you. And we're reaching 90% in many demographics. Finally, the top one, the red line, shows the likelihood that there's up to 4 other people just like you. And basically, we have covered nearly every American inhabitant now. I reran this number for Germany as well, and we fall into similar percentage ranges here. And because of what I just showed you, information like age, education, ethnicity are called quasi-identifiers. They're not identifiers such as name, but a combination of those is often enough to uniquely identify a person. Let's take this as our example data set for the second third of the talk. Let's say you're a researcher, you went out, asked people, if today was Sunday, which party would you vote for? And you note down some demographics of the people that you asked, and you note down what they would vote for. And now you want to make this data set available to some other researchers. We can see here 4 quasi-identifiers. That's if it's a man or a woman, the age of the person, the location where they live, and their profession. So if somebody knows all of these 4 things, for example, about this man who is 27-year-old, lives in Leipzig, and works in sales. If you know that this person is part of this data set, you can uniquely identify him by just looking into the data set, looking for his quasi-identifiers. And we call this attack a record linkage. Given the quasi-identifier information you have, you can point to one or very few records in the data set. And to protect ourselves, we can just say, given a combination of quasi-identifiers, we want that this combination points to several records in the dataset. Particularly, we want to have it at least k records. And this combination of quasi-identifiers we're going to be calling equivalence group for the rest of this talk. So let's get back to our dataset. We have, So right now we have a k of 1, because in this case, every record, every group is just 1. Like with every combination of quasi-identifiers available, you can uniquely identify one of the 7 people in this data set. So let's try to anonymize that and raise k to 2. And we have a bunch of ways. I'm going to talk about 2 today. That is generalization and suppression. So our salesperson from Leipzig, maybe it's not that important that he is from Leipzig. Maybe it's just good enough to write Saxony. And maybe then we can group him with other salespeople from different cities in Saxony. We can also generalize other attributes. For example, numerical attributes, like age, you can put into nice ranges. So instead of writing that our salesperson is 27, you say our salesperson is between 25 and 29, or is between 20 and 29. And we actually see in our data set, we have another salesperson also from Saxony in a similar age range. So we could just go ahead and move this and generalize both attributes, age and location. So they are no longer their exact age, they are between 20 and 29 and live in Saxony. We have 2 others who are quite similar. They are both women in their 50s who live in Heidelberg and work in some kind of engineering. We can generalize this as well. We have these 2. They're not super similar, unfortunately. The only thing they really have in common is their profession. So if we do this, we're going to lose a lot of information. We don't know anymore if they're a man or a woman. We only know they're in between 40 and 60. They work in some kind of craft, and they live in Cologne. And finally, we have our nurse 23 from Potsdam, and she doesn't really fit in with anyone. And maybe it is for the better in this case to just suppress her record from the data set. And whether to go with suppression or generalization, of course, there's always different options. So maybe for the last 2, we should have suppressed as well. Maybe that we would have kept more information in the data set in this case. So when you run algorithms, for example, for k-anonymization, you can often say how much you want to suppress, how much you want to generalize, and you give some thing that you want to optimize, for example. You want to optimize for information loss. So, yes, every combination of quasi-identifiers that is in the data set is now in groups of 2. So k is 2, success. But we have a bit of a problem. Because in this equivalence group, both people would vote for A. and you don't need to be a genius to figure out if you have this information about your friend from Heidelberg that she would vote for party A. So we call this attack an attribute linkage. You cannot pinpoint to some specific record, but the distribution of the sensitive attribute in the data is such that it's very easy, that it dominates the equivalence group, and it's easy to figure out the sensitive value. So you can call now for L diversity, meaning there must always be L distinct values for each of the sensitive attributes in an equivalence group. So in this group, it's fine. There's two different parties. If you just know that your friend from Saxony who works in sales is in the data set, you don't really know if they would be voting for A or C. But as we said, here's a problem. In this case, we have an L equals 1. And remember how we said that everybody has the right to the same equal privacy? Well, we need to go with the worst case scenario here then. The overall data set has an L of 1. So let's try to anonymize that such that L equals 2. And one way to go, we could, for example, generalize further, group these 4 together, and we kind of lost most of the information content of the data set. And we're not even safe yet, because we have an L equals 2, but 75%, 3/4 of these rows would vote for A. So we still have a dominating value for this equivalence group. So there's also what is called T-closeness. So the distribution of the attribute over the equivalence group should be quite similar to the overall distribution. That means if the overall distribution of party A is 75%, then that should be fine. The problem is this is what we set out to find out, right? We wanted to know which different demographics vote for which different parties. And if we now say that every equivalence group should follow the overall distribution, we can't really figure out anything anymore from this data set. On the other hand, this was a toy example, only 7 rows, so obviously we're going to lose a lot amount of information trying to group very different people together. So I went ahead and did some experiments. I used the standard machine learning data set called adult. It contains information on people's age, on their education, on their ethnic background, and the class value is whether they earn more or less than $50,000 a year. I used the RxD identification software to perform anonymizing operations. I used the standard settings, which is in particular interesting. It tries to minimize information loss. And after the dataset was anonymized, I just ran a logistic regression to figure out if classification performance suffers. So on this, in this plot, you see on the x-axis the different values for k. This goes up to a bit over 500. And on the y-axis, you see classifier performance. I'm using here the F1 measure. So you want the higher the number, the better. And we see that for about up to k equals 50, we're still pretty good. We're not losing much. We're still reaching similar F1s as previously. Afterwards, the F1 starts dropping and is quite much. It is basically at half of previous performance for k around 300. One thing you should keep in mind that this is for one specific data set and for one specific classifier. That doesn't necessarily mean that this is generalizable, that k equals 50 is a good value. Also, what happens here? I increased the k a little bit, and now suddenly the F1 is absurdly high. It's even higher than what we initially set out for. So let's dig into this. How did this happen? One thing I looked at first is how many values we have for each attributes. So we said, for example, we could group ages into ranges. So if we have ages in years, we have, let's say, 100 possible value. If we have ranges of 10 years, we only have 10 possible values. In this plot, age is the turquoise one, and we can see for k equals 1, we have lots of different values for age, and already for k equals 2, these have been squashed down to just a few age ranges. The next thing that is being squashed down is the native country. And we can see what we expect. The more k we have, the less for each of the attributes, the less information, the less different values are left. We can also see suppression happening in this data set. So for k equals 1, we have about 30,000 rows, and as we can expect, a few rows every time we increase k will be suppressed. So in the end, we turn out with a little bit over 20,000 rows. So at first I thought we had way too much suppression going on, that there's maybe only a few hundred rows in the data set, and that is why the F1 was just so weird for high k. But it turns out, if we look at, this is k around about 1,300, this is all that is left of the data set. So basically we have made a statistics. We have a bunch of smaller groups of populations and very little class. We have dominating classes in most of these groups, very little groups where we actually have two classes left. So this data set has nothing to do anymore with the data set we had at the beginning, and we can't really compare the F1. Yeah, that was fun, but bad news. These methods, they won't really work for high-dimensional sparse data sets. Let's consider you're Amazon, and you want to publish a data set, one row for every customer, one column for the customer's ID. Let's have it a proper randomization, not just an MD5 hash. And then one column for every article you sell. And then you just make a little cross for every article that specific customer has bought. And it is quite obvious that with such a high-dimensional data set, you will have a very hard time grouping people. People are not that similar. There's such a wide range of articles they could have bought. Also, we don't have quasi-identifiers anymore, like age or education. Right now, everything is a quasi-identifier. As soon as you know a few things that somebody bought, you will be able to uniquely identify that person, that person's row, and figure out everything that they bought. And in fact, this has been done before. And a famous example is the Netflix price. So Netflix published a data set containing information on ratings that people did on the platform. And researchers showed that if you only know 2 ratings that somebody gave and the date that they gave that rating, plus minus 3 days, you can uniquely identify 68% of the people. That means if you ask your coworker on Monday what movies they watched on Netflix and how they rated them that weekend, there's a pretty high likelihood you can figure out everything else that person has watched on Netflix. Maybe a bit scarier is the case of the mobile phone location data. So these are data sets that contain information like when and where did you make a call. And when is only in resolution of 1 hour here, so it's not even super detailed. And this is data that all mobile phone operators have available. And it turns out you only need to know 4 of these spatiotemporal points to uniquely figure out for 95% of people in this data set all of their phone history. And because of this, researchers have called for an alternative understanding of privacy, going away from these quasi-identifiers, equivalence groups, and just having this really strong notion that if you're in the data set, your risk to your privacy should not substantially increase. This is a bit fuzzy. I think with an example it will be more obvious. So instead of releasing data itself, we're moving to a model of interactive queries. You cannot, instead of counting how many, what is the average age of people voting for B on the raw data set, you just have a query interface and you can give this question, you could also ask how many people in Potsdam voted for B. And the answer you will get is the actual result plus some appropriate amount of noise. And it's quite obvious why you need that noise. Assume you know your friend from Potsdam is in that data set, and you ask a query, well, how many people are there in Potsdam? 1. How many people in Potsdam vote for B? 1. Well, there you got your answer, what your friend would vote for. So you need to add this noise to give different results. So the idea is that the query system keeps a history of all such queries and makes sure that privacy is not, the risk to privacy does not increase. Unfortunately, most of this work is quite academic. I'm not aware of any practical system that is in place. And also, we said earlier, right, that we wanted to publish raw data. And what we are doing now is quite near statistics. But on the plus side, it's statistic where you can define the aggregate. So you're not at the mercy of the data publisher, what they consider is interesting. You can still formulate your questions yourself. And there has been work to formulate existing machine learning algorithms in terms of these queries. Let's get back to the practical side of things now. Unfortunately, like I told you, I can't give you a one-size-fits-all manual. What you should do is look at what data do you want to protect? And what happens if you don't protect it? What is the risk to your customer? Is it risk of their, is it criminal risk? Is it information like medical information? Based on that, you should figure out what kind of knowledge, what methods could your adversary potentially use? And also think about what is the use case of your data. Do you want people to be able to make visualizations, or do you just want to give to be able to do some statistics on the data? And based on these 4 questions, you should also consider, after anonymization, is there even enough utility left? Is it worth publishing the data set? There's a few red flags you can look out for. Obviously, names, addresses, phone numbers. Locations of any kind are critical. Remember, members of small populations. We talked about the older people previously. If you have ages, then there will be only a few people of higher age in there. And obviously, look out for untranslated text. They could contain information about the person that you're not even aware of. I looked for standards that people use. I found, unfortunately, very little. One of the highest privacy standards I found is the new medical laws in the US for publishing medical data in response to this medical breach that we talked about earlier in Massachusetts. Now you can only use the first 3 zip codes, first 3 digits of the zip code. You are not allowed to give dates as a full date, only years, and you need to group people ages 90 plus into one range. And obviously no names, phone numbers, and social security numbers. And the other one I found is actually, unfortunately, it's for statistics. So if you look on the internet, you will find the Eurostat, for example. They have a bunch of regulations on publishing statistics, which is not really what we are talking about here. But in the census in 2011 in Germany, there basically was a requirement for K anonymity with K equals 3. So for each equivalence group, there must be at least 3 records, otherwise completely suppress those records. So for the video, these are my references. And to summarize, what is insensitive to you is not necessarily insensitive to somebody else. The best method you can choose is dependent on your use case, your threat model. There is, unfortunately, a trade-off between anonymity and data utility, and many methods break down for high-dimensional data. If you're a data scientist, you apply some of the methods that I talked about today, and you're still unsure, maybe consult an expert. Thank you.
Questions?
Hi. Before you mentioned adding noise to the data, and how would you define doing that? Because obviously if you have one person voting in Potsdam, the smaller the data set, the greater the noise you have to add, which then you have no data.
Yes, that is true. It's very academic work, and they have proven some upper bounds. Let me just check if I will very quickly find this on what kind of noise you need to add. No, I'm sorry, I can't find that right now. But yes, the size of the data set is definitely relevant, and there's mathematical proofs on how much you need to add.
When you talked about red flags that you should avoid, you mentioned untranslated text. So how would you translate text, like in a different language? Or what would translated text
Well, that
mean
means,
more safe?
let's say you are a researcher from Germany and most of the data in there is German, but then suddenly somebody filled in the survey with some Turkish. You don't know what that contains unless you don't speak Turkish. So probably you should go to somebody who speaks Turkish and make sure that there's nothing in that text that identifies people.
At the beginning, you had this slide with graphs of age groups, not age groups, the age and the likelihood to pinpoint the individuals. And there was an interesting peak there.
Yeah, I have lots of slides.
Yeah, here, this
Here,
one.
yes.
Sorry, the
Yeah, well,
for age group 25.
Well, it seems like there's many people of that age in the US. So this kind of mirrors demographics. I also found that for Germany, you're safer if you're young because lots of young people who are students, for example, move to bigger cities, and generally you're safer in bigger cities because there's more people of your kind around.
Yeah, first of all, thank you very much for this very interesting talk. I'm wondering, whether this should also change the way how we store data and let data scientists access the data in our own databases. Yeah, so because as a data scientist, usually you have access to the raw data. Yeah, so would this imply that we should maybe also limit the access to the data scientists to blurry data?
Yes, that might imply that. I know there's some works on databases that work with differential privacy. So basically you have one trusted database and an administrator, but everybody who accesses the database can only ask these kind of interactive queries.
I love this.
Good exercise. Okay, so I have a question. Most of methods for anonymization involves bundling rare options, and how to do so to not introduce biases, not to erase information from rare diseases, places with not many people living there, etc., etc.
That is a very good question. I don't think I have an immediate answer to that. I guess you would want to, when I talked earlier about that you want to optimize for something when you anonymize, for example, for information loss, I guess you could define some measure of the biases in your data that you don't want to lose and use that as the criterion that guides your optimization of the data set.
One last question.
Maybe a generalization of this last question. In general, if you have this suppression when you have unique cases in your data set, sometimes they are the most interesting ones, the outliers. And in some sense, so if
I guess you got to live with that. And also, there's different schools of suppression. So you don't necessarily need to suppress the whole row, as I did right now. You might just want to suppress one of the attributes, and then maybe you're already able to group that person with some other people, and maybe that one you suppress is not this outlier that you want to retain in the dataset.
Okay, there is actually time for really the last question. Like Katharina is very efficient.
Can you give any advice on how to anonymize graphs on maps? So I have the problem that I want to anonymize maps of companies.
I don't have any with regard to that. No, I'm sorry. I know there's work. I know there's work in that area, but I haven't read into it.
So thank you very much, Katharina.
Thank you.